So let's talk about coding part in OpenFOAM. So we're not going to do any code development or anything in this basic version, but let's understand how the OpenFOAM is coded. Okay, that means how different applications and utility what till now we use with the help of different tutorials is coded inside the OpenFOAM environment. Okay, so before we exactly go towards that proper coding part, let me give you certain ideas about from where one can look at and how one can look at the deeper inside the OpenFOAM. So best way is to look at through the Doxygen. So this link I already shared with you. Okay, so this is the Doxygen for, let's say, version 3.0. okay, and with the help of this Doxygen you can walk through each and every utility, each and every application, each and every libraries that is available in src file. Everything you can walk through with this particular nice GUI based Doxygens. Okay, so let's say we started our calculation with the simple form. Okay, so let's explore how we can search that particular file. So simple form, when you search here, this file is appear. Okay, so simple form reference is here. Okay, if you want to go towards its source code file, then type it, go like this way. Okay, and you straight away going to enter inside this, and not only that, going to tell you where exactly you are. So application, solvers, incompressible and simple form, and then you can see certain important files and entire its code. Okay, so this is how one can go towards exact programming. If you go little bit ahead, okay, you can see all the different solver that is available in incompressible area. Okay, and everything is linked with the src folder. Everything linked, that means in the pimple as well in let's say in shape optimization type of the things, we are linking everything to the src folder. Okay, so that is what you can see. It's a simple, then in the simple different code is available in that same folder, like CreateField, that is include file, p.equation.h include file. Okay, u equations include file. So all this thing is available, so you can quickly walk through each and every entry of the entire source code. Okay, so later on we try to look at with this, but first let me quickly give you the idea how exactly the OpenFOAM this src directory and the application or utility directory look like. So for that, let me go towards install area. Okay, so where exactly the OpenFOAM is installed. So I am exploring the OpenFOAM 3.0x, and if you look at this, all the folders is available. Right now we are interested in application area, so go towards that. In the application you have a few more things like solver and utilities. Okay, so let's first explore the certain utilities and how it is exactly the coded. Okay, so that is sometime we use out of this certain utilities. So let's, here we have a certain utilities related to the post processing, pre-processing, mesh generations. Okay, so let's say post processing, and we are interested in certain let's say calculation near the wall. Okay, so here is the area where you can find out the what different utility is coded, and inside that, let's say we are interested how we can calculate the wall gradient or wall heat flux or wall shear stress or the y plus value. Okay, so let's look at wall gradient. So wall gradient, if you open, okay, you will find very important one file is called the .c file. So .c file possesses all our basic code, and through that C file we try to include multiple .h file. That is the idea. Along with that, you can see the make folder. So make folder facilitate us to link all the supporting libraries that is available in the src folder. So if you go here, make file, make folder, you have two files. One is the files and another is the options. So let me open both the things. Okay, so options first look at. So with the help of the options, you can link all the required libraries. Okay, so we try to include all the important libraries like this way. Okay, so libraries lib src, finite volume, and the include. Okay, so in the finite volume there is a ln include folder, and whatever the ln include folder possesses all the things we can link here. Same way in the mesh tool there is a linked ln include folder is available. Whatever is there we try to link here, and based on that linking only we able to access all the required libraries, like meshing related libraries, all the discretizations, everything. If you want to access here, we have to link. Let's say we want to utilize certain turbulence model quantity, then we have to link turbulence model. We want to require, let's say, some multi-phase related thing, then we have to include all the dependent libraries we have to include in the options folder. Okay, then another is the look, this is the exe included and this is the library included. Okay, so here generic patch field, finite volume, mesh, all these things we're going to include as a library from here. Okay, and this is includes allow you to access all the .h file that is sometime we required for our calculation, that is available in ln include. So let's first go to that area so you quickly understand what exactly available there. So let's go to the src folder. Okay, finite volume, and then you have a ln include file. So look, ln include give the shortcut to all the required .h files. Okay, by including this one line you have access to all this required files. Okay, and it is in line with the our entire code that we're going to build on this include files. Okay, so this ln include and all this include facilitate us the important libraries, important let's say some .h file, and everything is aligned with our particular .c file. Then we have another in the same Mac directory we have files. So files, so it facilitated us to create either library, executables, or dynamically linked library, everything. So here we can use the .c file, so that is our main source code. So here you can see this is vol grade u is our source code. So we try to use .c file and going to create a application bin. So it allows us to create a application. There is a library bin, so it allows us to create a libraries. Okay, so there is a different version. So one is the application bin, another is the library bin. So all the application goes in the application bin area. Okay, so if we open let me so this is application bin. Okay. Sorry. So this all the applications, okay, is available in this application bin area. Okay, like from mesh to fluent is one of the applications. Okay, so in all the applications whatever we want to use, like simple form, pimple form, everything is goes under the application area. So it is available at the application bin level. Okay, then you have a library. Okay, so if you go towards library area you get all the required libraries. Okay, like turbulence model, two-phase flow, all these libraries is available. And where we are here inside the our install version, there is a platform, and inside the platform we have a compiled version of the things. So look here, Linux 64-bit, GCC, double precision, and Intel 32-opt is the because I am using Intel, so it is coming with that. Okay, if you have some different version, then it will coming with that version. Okay, so all the compiled thing is available at a library level or at a bin level. Okay, so both will give you the idea. So whatever we compile, it goes here by default. Okay, but when we want to develop our own code or we want to modify this utility, don't directly create the file inside these two folders. So normal idea is that we cannot change anything that is available inside the OpenFOAM 3.0x folder. That means that is our parent installation. We don't want to compile anything within this folder. So normally how it works, we try to create our own utility if we want, then we try to copy the required utility, let's say this gradient. Okay, let's say we want to calculate the gradient of t in place of gradient of u. We add up this utility, copy in our area, and then before we go for compilation, in place of form application we say form user bean. Okay, and with this flag value, what going to happen, in place of keeping this all the things at this area, it try to keep somewhere else. Where it going to keep, I will show you. Okay, so in place of this, it try to compile in the your home folder. There is a, based on your username, it try to create L Ubuntu is the username -30x. Why? Because this is the OpenFOAM version. Inside this, they again construct the platform same, and you again have a two both the things. Okay, so got it. So by default, if you don't have this user flag here, it goes inside the this area, sorry, exactly at the this area. Okay, here in the our installed OpenFOAM. But if you don't want to keep, or it is not wise to compile our own source code in this area, at this location, so better way is to keep everything at this area in our own. Let's say what, based on your username, it try to create this particular folder. Inside this folder you can see the again platform folder, and then again you have a this version folder, and again you have lib and bin, both the files. Okay, so it possesses my own compiled exe files. Okay, so as well as if you go towards lib, okay, it gives us the idea if I created any new libraries in it. Okay, so this is after I compiled the swag form and everything, this all new libraries is created here, like lib groovy bc. Okay, it is not coming with the our actual distributed version of the OpenFOAM. It is coming, it is the part of the another adapted version of some utilities. So whatever you compile by your own way, it going to so it will transfer into this particular folders. Okay, so please remember, by default everything goes inside the let me again go to the area inside the OpenFOAM 3.0 platform and the folder. Here you have a two folder, or if when you want to compile your own thing, then it's supposed to go at a L Ubuntu based on your username, platform, and this area. Okay, so there is a vast difference. So you cannot compile while you are adapting the new utility, creating your own solver by form application beam. That is wrong. Okay, you cannot do that way. So better is the form user application beam. That is the best option. Okay, so this is how you can set the file and options. Okay, so again options facilitate the linking of the all the required libraries. Okay, and the files is the directive of the .c file, and what is the name after the you compile the .c file. So this is the name, and with the that name, when you type this name on our terminal, you get this exe file. Okay, or the executable. With the help of that, you can run and calculate the wall gradient. So this is how you can find out the our compiled version of the things. So this allow us to facilitate the name and the create the executed or application or the library based on the .c file. So that all the things is available in the files, and the relative related all the supporting files, options, files what we want to link is goes in the option folder. Now after that, let's look at our .c file. So when you look at the .c file, it gives you certain descriptions. Okay, so calculate, let's and write the gradient of u at the wall. Okay, so it try to write the gradient of u that is at the wall, and then first file we going to include is the fv cfd.h. Okay, this is the very important class of the files. Okay, and it possesses all the required include files, like it give you the idea about the time, all the discretization methods, everything is you can access with the help of this fv cfd.h file. So let's quickly explore what is available in this particular file through our Doxygen. So here just type fv this file. Okay, so look, when you open this file, inside this it give you the certain ideas. So include dependency graph of fv cfd.h file. So when you call this, what is aligned with your entire code? So time, fv mesh, fvc.h, fv matrix, fvm, linear, uniform dimensions, calculation of fv patch, all these required things is aligned with the only one calling of this fv cfd.h file. So in the most of the applications you will see this file, because wherever we required all this important other library to be linked, we have to call only one single library, fv cfd.h. okay, let's explore this individual file. So if you look at the time.h, if you click, okay, so it gives us the certain its description. So class to control the time duration OpenFOAM simulation, okay, and if you go towards more, it give you the more detailed idea. Okay, so it try to time.h file try to create and try to control all the time respective all the coding with the help of this one file. Okay, then fvmesh.h. okay, so fvmesh.h, what it possesses, it give you, or it facilitate all the polymesh related files, as well as let's say all the data handling, everything related to the meshing it try to handle. So if you look at its information, so it contains all the topology and geometrical information related to the mesh. So let me enlarge. Fvmesh contain all the topology and geometrical information related to the mesh. Okay, so all the information that is required for the mesh manipulation or importing, exporting mesh, everything is available in the fvmesh. So it is one of the very important files. Okay, and it try to link the polymesh and so many things. So this is the entire tree. Okay, you can walk through one by one file and try to get exposure how and what each file possesses. Okay, what informations. Okay, let's go back. Then another fvc.h. So this fvc.h and fvm.h is two very important file. Okay, so let's explore this. So fvc.h, what it possesses, FVC surface interpolation, volume integration, surface FVC surface integration, averaging. Okay, then DDT term, then D2DT term, divergence, flux gradient, sun gradient. Okay, Scroll, Laplacian, source term. Okay, all this thing is possessed inside of this fvc.h. okay, but what its definition? Function to calculate explicit derivatives. Okay, so when any of the derivative you want to take as a explicit, so you supposed to write a fvc as a class, and based on that you supposed to take the derivatives. Okay, what I mean to say, if you want to understand, let's go to the code side. Okay, so it not available here. Let me open the simple form solver, incompressible simple form. Let's explore this file. Okay, so here also our first file fvc.this. Later on we explore this entry, but what I mean to say, if you go to u equation and the p equation, we come to know. So u equation, you remember that we have a certain terms like divergence. This is convective terms, so we taking convective term as a fvm. Okay, same way mrf, all these things forget right now, but another term is the gradient term. Okay, so that we are taking with the help of the fvc. So what it mean? FVC is belong to the explicit way of treating the any of the PDEs. So what it mean is, says that the pressure we are treating as explicit variables. Okay, and if we go back and go towards the fvm file, let's say. Okay, so fvm allow you to do certain operation, ddt, d2dt, divergence, Laplacian, and the source. Okay, but it try to take everything as an implicit way. So what it mean? It mean that we are taking the velocity as an implicit way and the pressure as an explicit way. So that means we are taking the pressure from the old or old time step. Okay, and based on that we try to calculate the velocity, but when we are calculating velocity, we are treating the velocity as a implicit way. Okay, so whatever the term you want to take as a explicit goes with the FVC, whatever the term you want to take as a implicit, it goes as a FVM. So please understand these two difference from this particular thing. So when we go, let's go back again to the FVC. So FVC belong to the implicit treatment, okay, sorry, explicit treatment, and the FVM belong to the implicit treatment. And what it give us, it give us the all the interpolations, everything, okay. So let's say we want to explore how the divergence or the flux or gradient is calculated, then you have to go towards this area, okay, and then from here it gives us the certain ideas. So it gradient, so different class, this is all the operator overloading type of this function. So it, with the help of the same function, you can calculate the gradient for vector, scalar, and everything, okay. And entire source code is available at these locations, okay. So you can explore with the help of the Doxygen very nicely, okay, each and everything. Then so this is one of the very important file, FVC, okay. Then FV matrix, if you go, so it try to look at the scalar matrix and FV matrix, both the things, okay. And how it is calling different things is also available with this FV matrix.h, okay. So it allow you to generate entire global matrix, okay. So after with the help of the different class of the discretization methods, okay. So it is a very important let's say file. So sparse matrix type and solver designed for finite volume solution of a scalar equations, okay. So FV matrix is take care of all the matrix related stuff, okay. And if we look at here, its location is in the finite volume FV matrix, its locations. Then we have a FVM. So FVM, as I told you, it's dealing with the implicit derivatives, okay. And let's say we want to look at how exactly the divergence is going to be calculated, okay. So divergence, if you want to calculate, we require the surface interpolation schemes, okay. So surface interpolation schemes, it going to call, and based on the whatever the scheme we selected, it try to look at the discretizations. But idea is that it try to treat everything as an implicit derivative ways, okay. So this is certain its codes, so you can walk through it very nicely with the help of this, okay. Then we have a linear, then uniform dimension field. So it try to check the dimensions of the all the variables and everything, calculate FV patch fields, okay. Fixed value FV patch field, calculated FV patch field, fixed value FV patch field, this belong to the boundary condition area, okay. Fixed value FV patch field, so field types, okay, and it give us the how to exactly apply the boundary conditions. So that is belong to that part, okay. So if you remember, when we talk about the boundary, I guide you from where you get the all the boundary information. So finite volume fields, FV patch field, basic and fixed values, okay. So it is belong to the fixed value, so it is here. If you go towards the basic, okay, so you have a zero gradient, fixed value, mixed, calculated. So zero gradient, if you go, it give you the idea how exactly it is coded. So if you want, you can walk through from this side also, okay, and you able to enter inside the that particular coding as well, okay. So Doxygen allow you to go in each and every line of the source code. So it is a, I say it is a very effective and very important tool to look at a time everything, okay. So then we were okay, so this is about the FV cfd.h file. So let's go back again to the area from where we started. So this is one of the very important file, and you come across this file so often, okay. So you supposed to have an idea what it possesses. So ultimately it give you the entire inclusion of all the important class, okay. So if we open that file, you come to know that it facilitated time, FV mesh, FVC, FV matrix, FVM, linear, okay. All the important include file we can include with the help of this simple and very straightforward include option fvcfd.h, okay. So this is one of the very important file. Then if we want to look at this utility, okay, so we want to calculate the wall gradient, okay, of u. So when we want to calculate wall gradient of u, definitely we have to read the required field. Okay, so we are reading the field with the help of the u header. Okay, so we are reading runtime. Okay, then so ultimately we going to read this particular u file. Okay, u is the vector, so we have a volume vector field. Okay, so first we create the object of it. Okay, and then we created, then when we want to calculate this wall gradient, so it is the gradient we have to calculate. Okay, and that is very simple way you can calculate for a boundary. Okay, u boundary field, because it is a width related to the boundary. Okay, and whatever the patch we want to calculate, so normally try to check the wall, whatever the places we specify the wall boundary condition, so they try to check either it is a wall or not. Okay, and based on that, if it is a wall, then this come here and try to look at the sun gradient, surface normal gradient. Okay, so if you want to calculate the normal surface normal gradient, this is the way you can calculate, and that is directly stored inside the wall gradient at a boundary. So because wall gradient we want to calculate the boundary, so it is a boundary phenomena. Okay, so quickly one can write it with the help of wall gradient dot write options. Okay, so this is how one can quickly walk through this very simple utility. So I suggest spend couple of hours time. Okay, and try to go towards so many utilities that is available, like here is the wall, then y plus, how the y plus is calculated. Again, when you look at the y plus, go to the make file, look at this both the options. So look, now y plus we want to calculate, that is related to turbulence, so definitely certain turbulence related libraries we required. Okay, so all this thing going to include from this place. Okay, so and this is include file, and this is respective libraries. Okay, so include file gives you the path, but after the compilation of that particular all the files, some libraries is created. Okay, so it is fall under the library area. So turbulent model is one of the libraries. Okay, finite volume is the library. Okay, meshing tool is the library, sampling is the library. Okay, fluid thermo models are the libraries. So all these belong to the libraries. So this all the libraries one can check very quickly. Okay, so let me guide you to the area. Let's go to the here, then platform, libraries, tree -L1. Okay, so this is all the libraries, like library two phase property. Okay, then lib of turbulence model. So lib turbulence models. Okay, this is one of the libraries, and this is what we are try to link like this way, lib turbulence models. Okay, so this is the library. When you say, so it try to search inside of this area. Okay, in the lib. Then we have a lib mesh tool, let's say. Okay, so all that is here, lib mesh tool.so. so this is dynamically linked library. Okay, .so, that means while the any application utility is executed, at that point of time only it going to link. Okay, like lib OpenFOAM.so. Okay, so all these libraries, whatever we want to link, okay, we have to write it down here. So sometime what happen when we are developing our own solver, we at the before and we don't know what library required and what we supposed to include. So normally what I follow is something like this: whatever the most relevant application or utility, we're going to start from that area. When you're going to start from that area, it is always possible that all the required libraries is available, but sometime then it is still this all dependency we have to resolve. Then we have to look at some detailed way, and we can, based on the error, we can try to linked appropriate libraries. So that all exercise we will do when we talk about the programming modules. Okay, at that point of time it give you the better idea how to do that. But right now please understand, this particular options file facilitate all the required includes files and all the libraries. Okay, that goes very nicely with this. And if you want to see what different includes file is possessed in this particular area, then just go to this location and look at the include file. You come to know what is available within that. Okay, so this is how one supposed to go towards each and every utilities. So if you walk through as many as utility, you come to know how it is coded, what different look. Now FVC, then we also require the single phase transform model because we want to look at the new, then turbulence model because we require the new T or that calculation. Okay, then turbulent fluid thermo models. Okay, then new T wall functions F and near wall distance. So how to calculate the near wall distance and wall FV patch. So it facilitated the name of the particular wall. Okay, so like that way you can look at the different things with the help of this. So Y plus calculation. So Y plus is the very important quantity for turbulent calculation. So normally we fix based on the Y plus, we finalize the our near wall first cell height, and when we simulate after that we must check the either Y for Y plus value, whatever after the calculation we are getting is as per our log law or not. Why I'm saying that, if we are working with the let's say standard wall type of the treatment, okay, then our Y plus must be greater than 30. If not at the maximum places, then we have to work with the mesh. Same way, if we are working with low Reynolds number type of the treatment, then our Y plus must be at least near to the 1. Okay, if it is more than something like 11.25, then it is wrong. At least it is below something 1 and so that is all the things we can check with the help of this Y plus utility. But idea is that with the help of this you can create your own utility as well. Okay, so let's say in some of the calculation you require the Y plus for your own utility, then add up that thing from this Y plus calculator utility. Okay, then wall heat flux is another very important utility. Same way, make file, look at the options. So when you look at the options for this, again we require the turbulence model, everything is available. Along with that, finite volume and mesh is required. Then we have it is application bins user form application bin, and this is our .c file, and with the help of that we are creating the wall heat flux as a one of the utility. But if we go here, in case of all previous utility, we have additional file, CreateField file. Okay, so let's explore this thing, so it gives you the idea. So same way, fv cfd.h is first one, then turbulent thermo model required, solid thermo required, wall patch is required. Okay, along with that few more files. So add zone, set root, create time. So this all thing is automatically taken care after we include this file and the few more entries that we kept in this include and this library file. With the help of that, all these files whatever we required, okay, it in line with the our code. Sometime let's say a few more entries we required here. Okay, so you by mistake you added few more include file, and when you compile it and respective libsrc or the library file you didn't include in the options, then it will give you the error at a compilation level, it is not available. Okay, or that type of the error. Then you come to know that, okay, this file required certain dependent libraries, so that path you supposed to include here. Okay, so that how one can check. So let's say you don't know which particular include file you can include, so that you able to resolve that particular error. For that purpose, you check what different utility or application possess the similar type of the file, and check its option area, and respectively you can add the file inside the your options area. Okay, so like that way you can quickly resolve the required dependency. So while we are working with the OpenFOAM, very important aspect, how we can resolve this dependency, because to resolve the dependency we require the certain linking in the this particular option file, and if we don't give the proper instruction to option file, it will not going to link appropriately. Okay, so please make sure all your required files is included in the options area. Okay, then we have another file included, CreateField.h. okay, so that is the part of this code. So CreateField, field says all the variables. So with the help of this create field, what we're going to do, we try to create our all dependent variables and all the transport property, everything you can read inside this create field file. Okay, so like we are creating the volume vector field as a u, we are reading, okay, must read, auto write with the help of the definite mesh. Okay, so all these things is come under this create field area. Okay, so create field facilitate ultimately all the field variables and important property you can read and create the respective fields in this particular files. Okay, so create field is normally go with most of the .c file. Okay, so .c file facilitate the basic code, and create field.h allow us to create the respective available required field and the required all the properties. Okay, so this is how you can look at the different entries. We require the wall shear stress. Okay, so and please understand everything is the dimension. Okay, so sometime we have to set some dummy dimension as well. Okay, so in some of the places, let's say when we are creating our own models, okay, or on some libraries, at time we have some constant, so at that time we have to create some dummy scalar dimensions inside this create field area. Okay, so later on we explore how to do that, but idea is that in this create field and with the help of this particular .c file, we can develop our own new utilities. So when you want to create your own utilities, try to adapt whatever is most relevant to your area. Okay, so sampling, okay, shear stress, turbulent, velocities. So velocities in this, you look at the verticity in the so verticity is how you can calculate the verticity. For that you have a calc.h and fvc.h file is included. Okay, so everything we're going to calculate based on the explicit way, so that's why we have fvc.h file included. Okay, so verticity is nothing but the curl of u. Okay, so we quickly say FVC curl u, it try to calculate the all component of verticity. Okay, and if you require the magnitude, just we type the mag of verticity and magnitude verticity created, and then immediately we write the both verticity dot write and the mag dot write. Okay, so it is very simple way we can create the different class of utility. Again, if you look at here, every places file and options to file whatever is required is available. Okay, so and depending on the requirement of the libraries or include files, we can include in the options and in the particular locations. So this is the few things as at a utility level you can explore. Okay, so I suggest please walk through as many utility you can. So turbulent, you have a Reynolds stresses calculator. Okay, so let's say sometime we want to calculate Reynolds stresses. Okay, so Reynolds stress R you can calculate very quickly. For that we have to first create the this particular, let me guide you, calculate compress. Yeah, so it is it is common for compressible and incompressible. Okay, so you can see multiple entries related to that, but Reynolds stresses is a tensor quantity. Okay, so we have to create appropriate tensors in this particular files. Okay, and it requires certain transport model and the turbulence model. Okay, so for that something is included very neatly straight away here. So few things you try to explore with this. Then data conversions. So data conversions, like if here you can see all the data conversions, that means you can import the mesh, okay, inside the this is post processing, so you can export the data from form to the respective format, like form to the tech plot, form to the fluent, form to the insight, all this form to the VTK, all this utilities is available. You go in any utility, try to explore. Okay, so my suggestion is that don't restrict yourself to certain utilities. Try to look at, go to the as many as utility you can explore so many utilities, how it is coded, and that is the way to learn the OpenFOAM. Please understand, if you want to work with the OpenFOAM, don't restrict yourself like you are working like a ANSYS or star CCM. No, that is not the best way to work with the OpenFOAM. OpenFOAM is all about the coding and creating solvers and customizing application utilities and all these things. So for that you have to go towards the coding environment. That is the way I can see. Okay, so this is all about the different utilities. Okay.